All right. Hello, everyone. I'm Ben Sachs. For those of you who don't know me, my company, Sachs & Associates, offers training in C and C++ for companies all over the world. And I'm here to talk a little bit about the basics of unit testing. So there's a lot to cover. I'd like to just dive in, but one thing to mention is that feel free to ask questions as we go. I will try and take them as best I can. But please understand we're on something like a 10 to 15 second delay. So it may take me a moment to see your question and respond to it. All right, let's get started. So automated unit testing is something that's become very popular in certain circles of development. There's a lot of books written on it. A lot of people swear by it. But at the same time, there are also a lot of developers who've never had the chance to do it, who haven't written any automated unit tests. And given that, the amount of information that's out there can seem kind of overwhelming from someone approaching it from that initial position. So, for example, if you look back at one of the previous CppCon talks on unit testing, they listed out 5 different properties of good unit tests. Correctness, that the test succeeds when it should succeed and fail when it's supposed to fail. That it's readable so that you can actually understand what the test is doing without extra documentation. Completeness, the idea that your tests cover enough of your program to provide you with a good sign that things are working correctly. Demonstrative, the tests serve as a model for how you would actually use the components being tested. And resilient, they'd be maintainable and useful over time. There's a fair bit to think about just there, and this is just one question. You also may find yourself thinking about what unit testing framework should I use, and there's a whole bunch of them that you could potentially choose from. There are other questions like, how do I avoid dependencies between the tests? How will I integrate this testing with my build process in some, say, a continuous integration server or something like that? How I measure how much of my code is actually being tested? Do I have a code coverage tool that I need to select? So all of that taken together can be kind of intimidating, and it means that it can put you in a very paralyzed position, because if you're just starting to look at unit testing, you may think, I'd really like to test this thing, but I'm not being paid to write tests. I'm being paid to get this thing shipped on Friday. So I need to make sure that I'm not spending too much time doing this. And the point I'm trying to make in this talk is that you can grow into unit testing. It's something that you don't have to take as one big giant leap. You can do it as a series of steps. So eventually all of these questions about which framework should I use, how will I keep my tests independent, those are things that you will want to address in order to get a really solid unit testing system for your project. But you can start without answering all of those questions. There are unit tests you can write before that. So just as I was writing this up, I thought of the saying from Lao Tzu, the Chinese philosopher, a journey of 1,000 miles begins with a single step. You've got to start somewhere. If you're going to write automated unit tests, one of them is going to be your first. And in this case, what I'll be doing is starting with an existing program that doesn't have any automated tests at all. And what I will show is we'll put a minimum amount of code in place to get an automated test running, and then we'll build on that. So, and the other thing I want to mention is this saying from Chuck Jones: every artist has thousands of bad drawings in them, and the only way to get them out is to draw them out. That is to say, there will probably be flaws in the first automated tests that you write. That's okay. It's part of the learning process. We expect to get better at this over time. So in some of these cases that I'm showing you here, we will start with a test that might have some weaknesses or flaws in it, and we'll gradually improve it over the course of this hour. Now, I mentioned that I'm starting with an existing program here. I'm doing that because I think that that's the situation that a lot of developers are in. We often, if you are looking at adopting unit testing early, you're working on some piece of an existing project. Most of us are not right at the point of starting up our next project right now. And so test-driven development, the standard model would be, before you write any new code for the project, write the test code. Do just enough to get the code to compile and watch it fail, run the test, and then once you've seen that the test fails correctly, then go and actually write the code that is needed to make the test pass. And once you've done that, once you've gotten together the basic code that needs to be there for the test to pass, then you can refine it and refactor it to improve the state of it so that the system is more flexible and ready for, well, the next test that you're going to write, basically. But in this case, we're not doing that because the program already exists. Now, that's not to say that test-driven development isn't a good thing to use. I like to use it when I can. I think writing the tests first has a lot of benefits. It helps you get a clear sense of the interface that you're trying to implement. It forces you to think about testability early on. And you don't have to do artificial work to make sure that the test fails later on. We'll see that a little bit later. But I also wanted to make sure that it was clear that TDD isn't the only way to write automated unit tests. I don't want you to think that, oh, just because I didn't start out writing unit tests from the very beginning, then, well, now there's no point in doing them now. You should still write the tests even if you weren't able to necessarily write them first if you want stable software. All right, so the program I'm going to use for this example here is, it's called Decal. And what it does is it translates basic C++ declarations into English text. It's taken from an exercise in Kernahan and Ritchie's original book, and they did not publish solutions in their book, but there's a separate book, the C Answer book by Tondo and Gimple, that does show solutions to those exercises. I'm not using their solution. I'm using their solution was written in C, but I'm using something based on that example. The idea is that you will type in a C++ declaration like this into standard input, and Decal will output a description of what that object that's being declared is in basic English. It will decipher this, it'll translate stars into pointer to, it will translate angle brackets into array of n elements, things like that. This will help, this is sometimes helpful for seeing the difference between, say, a constant pointer and a pointer to a constant object. And also just, it's a nice exercise for reinforcing what you already know about C++ declarations. Now, I didn't create this exercise specifically for this talk. It's actually taken from a series of articles written about 25 years ago. So you'll see that in the bibliography at the end. It's not exactly what appeared in those articles either. I've updated it to use some modern C++, but it's still very, if you happen to have read those articles, you will see some similarities. All right, so Decal reads in input a character at a time, gets rid of any white space, and it groups the remaining characters into tokens. So each token is a series of characters that forms a single symbol for parsing purposes. So here, int is one symbol, the star is a symbol by itself, the word P, that's a symbol by itself, and the semicolon is also a symbol. So, so I'll show you that breakdown in a little bit more detail as we go on. There are three main classes that are involved in the DECL program. There's a token class where each token represents a single one of these input tokens, like the word int, the star that represents a pointer, things like that. The scanner class, a scanner object takes in input as a stream of characters from a basic input stream and translates it into a series of tokens. And that those tokens are fed into a parser, which analyzes the sequence of tokens, figures out if they form a valid C++ declaration, and if they do, it translates that declaration into English. So there are two source files involved here, scanner.cpp and decl.cpp. The token and the scanner classes are in scanner.cpp. The parser class and the main function are in decl.cpp. So each token consists of two data members. There's the actual text of the token itself, and there's also a category that identifies what general kind of token this thing is. And so there's a special category, no more, that identifies the end of input. This isn't really a token, it's the indication that no more tokens exist. So when the scanner receives this input here, int star p semicolon, it will wind up generating these tokens in order. One for int, one for the star, p, semicolon, and then the very last one will be the empty string with the no more category, indicating that we've reached the end of the input, there are no more tokens left to read. So the token class has a fairly simple public interface. It consists of just the category enumeration type, some default copy operations, and then accessor functions for the text and category pieces. Its only public constructor is the copy constructor. So in general, tokens originate with the scanner. The scanner is the piece that creates tokens in the first place. Once you've received one, you can copy it around, but you can't really create them yourself outside of the scanner. So there are these two other constructors for the scanner to use to actually create tokens, and it has access to them because scanner is declared as a friend class of the token. The scanner and the token are really designed to work together closely like this. Scanner's public interface is just a constructor and two functions. The constructor sets up the scanner to use a particular input stream. Get reads the next token in the input stream. Current is just a way of fetching the last value that get recently returned. So once you call get once, if you keep calling current after that, it'll return the same thing that get returned initially. Once you call get again, it will move on to the next token, and current will then start returning that token instead. The parser class here has a public interface that's just a constructor that sets up the input and output streams for the parsing operation, and a single function here that just triggers the parse to go. Now what the parse function actually does is it can read multiple declarations. And it just reads them one declaration at a time, essentially, until the scanner runs out of tokens. So the first time that control reaches this line, when we're parsing this input, the token will be that int keyword at the beginning, which means that the token isn't the no more token, we'll move on and parse a declaration. Most of that is done inside this simple declaration helper function. It's a private function on the parser. And it will read until it finds a token that can't be part of a declaration. And if we're talking about a well-formed declaration in C++, that's going to be a semicolon that marks the end of the statement. This program is dealing with just declarations, not definitions, so it doesn't include support for initializers, int x equals 3. It just allows int x semicolon at this point. So the main function, all it needs to do is create a parser and then call the parse function. All right, so that's enough setup. What do we do about tests? At the moment, Decal doesn't have any automated tests at all. And there's a maxim that I've often heard programmers use that I'd like to come back to. Is what's the simplest thing that could possibly work? If we're starting from zero, rather than spend a lot of time thinking about different ways of doing things, just try to boil it down to the simplest elements and start at that point. Question, do you believe it isn't possible to employ TDD in existing projects with legacy code? And legacy being untested in this case. No, so different people would be more or less pedantic about what TDD actually is. Some people would look at one person might look at something and say, oh yeah, that's TDD. And another person might look at it and say, well, you're not really doing test-driven development because you didn't write all of your tests first one at a time, for example. Depending on how strict you want to be, some people might say different things there. I do think that it's possible to employ TDD in an existing project, something that didn't start from the ground up using TDD. If you're writing new components, you really can write the tests first quite easily. And if you don't write the tests first, that's not necessarily what everyone calls test-driven development, but if you're writing the automated tests, eventually you can wind up in a fairly similar spot because the end goal is the same. We want working code that has a bunch of automated tests that will ensure it keeps working tomorrow. So I think that you can use TDD in an existing project with legacy code, but it is something that has to be introduced over time. You wouldn't have the whole project suddenly become TDD based. Okay, so how can we add an automated unit test to Decal as simply as possible? So in general, the classes with fewer dependencies are easier to test. So the parser here depends on both scanner and token. Scanner and token depend on each other, but neither one of them knows about the parser. Scanner's public functions are designed to return tokens, and tokens can really only be created by the scanner. So they're designed to work together. It makes sense to focus our first test on the scanner and the tokens rather than on the parser, because they have fewer dependencies. So Decal knows that it's reached the end of the input when the scanner says there are no more tokens. That means the simplest possible test is if there's no input at all, the very first token should say there's no more input. That's our simplest test. So the body of the test is going to look something like this. Set up an input stream that represents empty input, create a scanner that uses that input stream, read in the first token, and what we should see at the other end is that token says no more. There's no more input. In a sense, there never was any input to begin with. So when we translate that into code, it's going to look something like this. That is, we know we're going to build the scanner around some kind of input. We're going to read a token from the scanner, and we're going to check to see whether the category of that token is no more. What we need to do now is figure out, okay, how are we going to represent empty input? How are we going to report success and failure from this test? So, with regard to the empty input, ordinarily, DECL is written to take its input from cin, standard in. Now, since this is going to be an automated test, it's not very automated if a user has to sit there and type in the input that we're intending to test. So that's not going to work very well for us. Fortunately, we've written scanner's constructor to work with any iStream, not just with standard in. So we can pass in another kind of iStream and use that as the input to the scanner. This is something that in the testing language is called dependency injection sometimes. It's rather than building the scanner to assume that it uses a particular input stream, we've built the scanner so that it can work in terms of any input stream that is provided by the creator of the scanner. And then, and this is something that generally makes things a lot easier to test because the scanner isn't making unnecessary assumptions about what other pieces of the code have to be there to make everything work. So, to create our empty input stream, we're going to use the iString stream type from the SStream header. And so we can, what this lets us do is just treat any string as if it were an input stream. So if I create an iString stream that looks like this, with the string 1, 2, 3, and then I can then read from that input stream into an integer, and it gets out the value 123. So in this case, all we need is a string stream that takes an empty string. We'll use that as our empty input for the scanner. By the way, one of the interesting things about this is that even if you're working on a project that has tight performance requirements where you might not necessarily want to be using streams all over the place or doing a lot of work with dynamic memory allocation, these tests are actually going to run in such a way that performance is somewhat less of an issue because they're usually not going to be running on a single computer. They're going to be running regularly in the background. So in order to do the reporting of the test, to report the results, we need to figure out how we're actually going to run the test. And this test is for the scanner, not really the whole DECL program. So we don't actually have to use the main function of the DECL program to run the test. We can build a different main function that's specifically designed to run this test. And then from there, regular old cout is fine as for reporting input, for reporting the output. We can just say, here's the name of the test that we want to run, scan empty input. So our result will be, when we get to the end, we write out either success or failure, depending on whether we saw the token that we were expecting to see. So, now normally I wouldn't actually put the test directly in main, and as you will see in a little while, I'm going to extract it and you start using helper functions. But for right now, I'm just keeping things as simple as possible, just to show you what you can do with the minimal amount of code. All right, so this version of main is in its own source file that I call decltest.cpp. So we compile that with just scanner.cpp. We don't actually need the original decl.cpp at all because it just contained the parser, which we're not using, and the main program, which we're not using. And when we execute this program, indeed decl test prints out, I tried running this test and it succeeded. because this is an existing program. There's a good chance that it may actually pass on the first run. That being the case, we're not quite done making sure that this test works yet, because test correctness is about more than just seeing the test pass when we expect it to pass. We also want to make sure that the test will fail when we expect it to fail. What that means is we need to now create a scenario in which the test fails so that we can watch it fail, because so far we've only seen it succeed. So there are lots of different ways that we could change scanner.cpp to make the test fail. As is often the case, there's often one way to do things right and lots of ways that something could go wrong. If you think about the human body as a system, that if your heart stops, lots of parts of your body are going to stop working at all about the same time. So that will represent a failure that could show up in lots of places. Ideally, we just want to make a single obvious change that will make the test fail, because if we'd been writing the tests first, then the test would fail due to a pretty obvious gap in the code. We haven't written anything to make it succeed, so that's a pretty obvious failure case right there. There's nothing wrong with doing something similar when we're going back and falsifying the test later on. I've heard this referred to as falsifying the test. I don't know how widespread that term is. That's just what I've seen used, and it seemed like a handy term here. Okay, so the get function for the scanner reads each token a character at a time. If the first character is EOF, that's how we know that we have a no more token. So inside the get function, if it sees that that character is EOF, it assigns no more as the right category for this token. So if we want to make this test fail, we need to replace that in some way so that we'll change that code, replace the value no more with some other value like identifier that represents a different kind of token. Then we can go ahead and run our test. And what we expect to see is now the test reports failure, because it's not returning the right kind of token on empty input. Now that we've done that, this is a pedantic little change. I realize that I've made it kind of trivial by using a fairly simple test. In reality, it's not always going to be that simple, but this just illustrates the basic idea that you want to know both that your test will succeed when it's supposed to succeed, and that it will fail when it's supposed to fail. Now that we've done this verification, we can go back, undo this change here, and restore the test to passing condition. We don't need to keep that change around. And in general, we won't need to falsify the test again unless the code actually changes. That is, the code that runs the test itself. So what do we have? Well, we have a test that uses no frameworks, no libraries. The full test code fits right on this next slide here. Just that. Now, and that code does one test, but it's actually fairly easy to take that and turn it into multiple tests. We can generalize this code into something that looks like this. I've changed it from the main function to a helper function called token test that takes in the name of a test, the text of a token, and the kind of token that we expect to see. And now, instead of printing out a fixed name scan empty input, it always prints out the test name. It prints out the test name. It creates as the input whatever text string it was given rather than just the empty string. And it compares the category to whatever kind of category was specified. And now we have a nice simple function for testing how the scanner can deal with pretty much any single token input. And I find this is not uncommon, where having written one test, that test turns out to serve as a model for a number of other tests. That's something that can happen fairly frequently. So it can feel sometimes like you're investing a lot of work in creating just one test. But then when you get to the end, you see, okay, now this one test can easily become 5 tests without too much additional work. Now, if I was going to have a full suite of tests for the scanner, I'd also want to include some tests of multi-token input. I'm not showing that here, but a real full test of the scanner should also be looking at whether the scanner works correctly when dealing with input consisting of multiple tokens. But what we've got so far is a pretty good start for how much work we've had to put in to make it. If these tests pass, it's a fairly good indication that the scanner is handling individual tokens correctly. It's not an absolute certainty, but in some sense that we're not looking for absolute certainties out of our automated tests. One of the ways I like to think about it is you're writing the tests not because the tests will catch all of the bugs that you might get, but rather it changes the way you think about debugging. Now the question becomes, when I see that a bunch of tests are passing, if I notice a failure in the code, then I can ask myself, okay, given that I know that all of this stuff works, where could the problem possibly be? How is it that all of these tests could say everything is fine, and I still see this problem over here? Changes the mentality that you'll use to look for the sources of defects. So in this case, we'd be able to focus our debugging efforts on the parser. We haven't tested that yet, so the problem could be there. Or it's possible that the scanner has some leftover state information in it after reading a token, and that for multi-token input, because we haven't tested that yet, that might be a thing that throws off the DECL program. But for what we've got, that's not a bad start. We've got, we've eliminated a fairly sizable chunk of the code as a likely culprit for a lot of failures, and we didn't have to spend that much time writing these tests. We didn't have to investigate using a framework or come up with how we were going to do a lot of work to integrate it with a build system. It's just, and so these tests don't need to take that much, they don't need to save us that much debugging time before they pay for themselves. Okay, question. How about testing private functions? These private tests seem convenient since you can't typically test for corner case inputs to the internal function by using the public interface. Yes. In general, the private functions are meant to be part of your implementation. You want to focus your testing efforts on the public interface of a class because it's the public interface that's going to be used in lots of different places. The private interface should be used in a relatively small number of different places, and you want to have a little more freedom to change the private interface, to change the implementation behind the scenes in order to deal with new situations that arise. Once I've written these tests, I may go back and modify the scanner to be able to recognize additional kinds of tokens or to be able to look ahead by a certain number of tokens. And that could involve a lot of changes to the private details of the scanner. I want my tests to focus on the public interface because what that tells me is then if all of those tests are passing, I know that I've managed to update what the scanner is doing without breaking any of those existing tests. Now, I don't want to be too absolutist about this. Sometimes, particularly if you're trying to introduce testing into code that has legacy behavior in it, that has legacy untested code in it, yes, you may find that there are some private functions that are used in enough places that it makes sense to test them. But in general, we want to focus on the public interfaces as the main testing that we do. And we want to write enough tests of the public interface that it also exercises our private interface in whatever ways we need to. Okay, so up to this point, we haven't used any kind of unit testing framework. This is just done to keep the work as simple as possible, see what kind of benefits we can get with a minimal amount of effort. So now let's look at if we add on the work of adding in a framework, what will that get us? Just the basic stuff with a framework. I'm trying to use a relatively small amount of the framework here and just show just taking the first step into using a framework, what sort of benefits do we see? And what other steps does that set us up for in the future? Again, we don't want to try and go all 1,000 miles at once. So in this case, I've chosen to use Google Test as the framework. Now, different frameworks are going to offer different features. So the features that I'm presenting here aren't necessarily universal. You may not find them in every testing framework, but they're certainly not unique to Google Test. You can find them in lots of just different testing frameworks. But in general, think of the stuff that I'm showing you here as a little bit more of a taste of what a framework can offer, rather than it will specifically be able to do this and this and this. So earlier, without using a framework, we created a separate main program to run our tests. And Google Test does something similar. In fact, it actually includes a main function that's pre-written, and you can link it in as a library to build your test code. You probably don't even need to write the main function yourself. So Google Test is distributed through GitHub at this address. Officially, the build system that it uses is Bazel. There's also CMake support provided on a community basis. It's unofficial. They don't promise that they won't break it, but it's generally pretty good. Now, exactly how you integrate your framework like Google Test into your build is going to depend somewhat on the details of your project, but it doesn't have to be particularly complicated. Google Test does build as just simple libraries, like these two specifically. All of the main testing facilities go in libgtest.a, and then the separate main program for executing the tests, if you want to link that in, has its own library. And then you can just link them into your project the same way that you would any other libraries. And you can go ahead and use Google Test. You may want to integrate it more deeply with your build system, call out to its CMake files from your own CMake system, for example. But you don't necessarily have to. There are ways of doing things fairly simply. Other frameworks, in some cases, are header only. There are ones that you basically just include the headers and you go from there. So earlier, the first test that we wrote was start with empty input, check to see that the scanner gives us a token that says category no more. So if we take that test and move it into the Google Test framework, it's going to look something like this. And here's what the different pieces of this are doing. So each test has a name that consists of two parts. The test here, capital T-E-S-T, is just a macro that assembles a function for running your test. And it names that function essentially based on these two pieces here. The first part, scanner here, is the name of a test suite, as we call it, a group of related tests. In this case, they're the tests for the scanner class. By the way, traditionally, I've seen these two, these names using capital camel case. That seems to be a convention. It's not a requirement. Well, Google Test is doing some work behind the scenes. So there are some restrictions on how creative you can get with these names, though. So empty input token is no more. That is empty input. The token is no more. Is the name of a specific test within that test suite that we're about to write. The code for running the test goes inside the curly braces, and the first part of it looks pretty similar to the way the code looked in the original version. Excuse me. The only difference is we don't have to write out the name of the test itself, because Google Test will take care of that for us. But otherwise, we're still setting up an iString stream that represents our empty input, passing that to a scanner, using that scanner to read a token. The part for reporting output looks fairly different. Before we had this, where we wrote an if statement and then manually printed out something to see out, in Google Test, it looks just like this. There's another macro, expect EQ, that takes two values. And what this is saying is we're informing Google Test that we expect these two values to compare equal to each other. In this case, it's testing that t.kind is equal token colon no more. And what this means is if that condition isn't true, Google Test knows that the test has failed, and it should report failure when it prints out the output of the test. So when you run the test, if it passes, the output's going to look something like this. It'll say, right now we only have one test suite with one test in it. So it will talk about it's running a single test from the scanner suite. That test is scanner, empty token is no more. And it ran and it passed. If it had failed, the output would include the real results of the comparison. That is, it tells us what the two values that were being compared actually were, which gives us a sense of a little bit more insight into, okay, what might actually be going wrong. I may not need to go into the code, modify it to have some output statements and things like that. I might be able to figure it out just from this message. So the failure would look something like this. And again, this one test we can expand that using it as a model for others, turn that into a whole bunch of tests. So we would call the test macro separately for each individual test, because that's what assigns a name to the test. But the expectation macros, things like expect EQ, and then there are others like expect NE for not equals, expect LT for less than, so forth and so on. Those work from inside other function calls. They don't have to be directly within the curly braces after a test macro. So we can put that code into a helper function and do something very similar to the token test function that we wrote earlier, that lets us generalize this test into just take in a certain text as input, build the scanner, read the token. We expect it to be some particular category of token. And now we have that one test has become three tests. And the output looks something like this. It's now indicating that all 3 tests are in the scanner test suite. So they're automatically grouped together in the output. And it just tells us the results from that whole test suite at once. Now, we can also filter this down. So if we only wanted to run a specific test, like the empty input token is no more test, we could apply a filter to the program. And that tells it only tests that match this pattern, which in this case is just a literal string, should be run this time that we run the decal test program, which is the name of our test program. And question, would you recommend using Google Test over other frameworks? For simple projects, very complex ones, what do I think? Google Test is a framework that I have a fair bit of experience with. It's also a fairly widely used framework, so that's why I picked it for this particular talk, was because it's fairly widely used. You can use a fairly small amount of it and still get some significant benefits out of it. And it builds nicely into some next steps that go beyond this one section where you'd start building into Google Mock and using that as the foundation for more advanced testing facilities. So I think it works well. I've had good experiences with it. It's not the only test framework I've used. I mentioned at the start, I also do training in plain C. Google Test is specifically a C++ framework. When I wrote my C programs, I went and I found a very simple little test framework called C Test, SEATEST. I'll put it in here and it can be copied over to the chat. And that's a very simple framework, very minimal, but it was something I could get up and running quickly, which is what I wanted when I wanted it. I think that different frameworks have different advantages. So which one is right for you is going to depend on the nature of your project, how many people you expect to use it, how quickly you think that the number of tests might grow. If you think that if you're not really sure and you're just tiptoeing into automated testing, probably get away with a fairly simple framework. If at this point you're fairly convinced that, yeah, this is something I want to do, I'd like a framework that gives me some good potential for growth, maybe you want to use a more advanced one. So I've had good results with Google Test, but it's certainly not the only one that you can use. And in fact, I'll mention a feature later on that some other test frameworks have that Google Test, to my understanding, does not. Okay. You can also filter using wildcards. So here I can run all the tests in the scanner test suite by just saying scanner.star. And now that runs all the tests in that test suite, doesn't run any tests in any other test suites if we had them. In this case, I just have the one, but you can use this filtering for that purpose. So up till now, we've only been testing the category of the token. We've been ignoring the text part of the token. We've just been assuming that if the category is right, the text that the token contains is also correct. Ideally, we'd test both, and we would report if either one of them had an unexpected value as a result. Now, back in our original test, when we weren't using a framework, we'd need to do a fair bit of work to expand the output code here. We need to have separate tests for each of the two different ways that the test could fail. We'd need to write out different error messages for each of those different possible failures. Using Google Test, or most other frameworks as well, it's fairly easy to add an extra expectation like this into the same test. So now this test makes sure that both the category and the text are matching what we expect them to match. I'll get to your question in just a moment. I want to finish out this thought. So now, because we now have two separate expectations in the test, Google Test's output will now give us an indication of whether it failed because the two kind values, the categories, didn't match, or whether the test failed because the token text didn't match. Here I inserted an extraneous space to make the test fail, which I knew that the scanner would ignore. Would you put all the test suites in the same file? Almost for a large for a project of any significant size, I can't imagine I'd put all the test suites in the same file. You know, if in a real version of this program where I wanted to have a full set of unit tests, or I wanted to have good unit test code coverage over my whole project, I would probably have a parser test suite as well as a scanner test suite. I would expect that at the very least, the parser's test suite would be in a different source file from the scanner's test suite. I would tend to place all of the tests for a particular test suite in one file. Usually, I try to keep my types fairly small so that I don't need to write that many tests. So we're not talking about adding a huge amount of code into a single source file for the tests. I can imagine, well, I don't need to imagine, I can say that there are certainly, I haven't stuck to that rigidly, and there are types that I have written from time to time where it might have made sense to split the tests out into multiple files. But generally speaking, I think of putting all of the tests in a test suite, in one test suite in a source file, and putting each test suite in its own source file. Okay, so what parts of Google Test have we used? Well, the test macro, the expect EQ macro, and the filter option. What have we got out of it? Well, we've got clearer, more detailed output from our tests. Our tests are now grouped into a test suite, which we can filter on what tests we want to run, such as down to a specific test suite, down to a particular individual test, things like that. And this is just scratching the surface of what you can do with a testing framework. So this gets you to a point where the framework is, you've started using the framework, and you can start gradually exploring the new the features of the framework as you write additional tests. Some of the ones that are a big deal are the notion of creating test fixtures, where you have several tests that use a common setup and teardown. You want to run several tests based on the same setup. A test fixture is a way of doing that without duplicating the setup code. randomizing the order of the tests. This is something that we see people do so that if the tests always run in the same order, it's possible that would mask certain kinds of failures, that the second test only passes because it came after the first one. If you randomize the order of the tests, that can help you identify those sorts of problems and notice when a test isn't cleaning up after itself. And then there are some frameworks that can actually generate the tests automatically. This seems to be a feature in particular of commercial test frameworks, that they will be able to automatically generate several tests along similar lines based on some information that you give them, and figure out ways of testing your interface in an automated fashion. Now, this is also a good point to take a step back, review the properties of what makes a good test. They're correct, pass when we expect them to pass, fail when we expect them to fail. They're readable. That is, you don't have to look at, you don't have to document them in much detail other than the code itself. It should be fairly self-documenting. We have enough tests to give us a reasonable degree of confidence that our code is working correctly. They're demonstrative. They represent how someone would really use this component in the main program, and resilient. We don't have to constantly fiddle with the tests and change them all the time to make sure that they stay up to date. We only want, you will have to do some test maintenance. That's to be expected, because we don't always get our interfaces right the first time, but that should be the exception rather than the rule. If you have to spend a lot of time maintaining your tests, it starts to become more questionable whether they're really saving you time. So, getting comfortable with those properties is an important part of the next big step in testing, I think, is moving into the use of mocks. Mocks, or other test doubles, as they're sometimes called, which are tools for minimizing dependencies between the tests. So I mentioned the idea that we could have a separate test suite for the parser as well as the scanner. Right now, the parser uses the normal scanner, the same scanner that we've been testing up to this point, to do its work. What that means is, if we write our parser tests to use that scanner, and the scanner has some kind of failure in it, it might look like the parser isn't working, even though it's really a problem in the scanner. It's not narrowing things down as much as it could for us. So by using a mock scanner instead of the normal scanner, we would be able to test the parser independently and make sure that a failure in the test would represent a real failure in just the parser, not the scanner. Okay, that brings me to the end. There are a couple of questions here. Does Google Test have the ability to show test coverage? When I've used Google Test, I've measured the test coverage through an external tool, but I'm not certain it doesn't have one. There may be one, and that system was just using another test framework or another code coverage measurement tool that we already had in place. For some functions that have dependencies on others, what framework do you recommend to easily mock these internal functions? So I typically think of mocking classes rather than individual functions, although you can do that. some mocking frameworks will let you do that, I should say. I've had good results with Google Mock. One of the reasons I picked Google Test as this was because Google Mock is a nice extension onto that. So it easily sets you up for this next step that I'm leaving you with a little teaser for. But there certainly are other frameworks that have mocking capabilities. Not all of them. There's C-Test, the C testing framework that I mentioned earlier. As far as I know, doesn't have any mocking capability. But so I've had good success with Google Mock, but I can't say that I've used enough different testing frameworks on enough different projects to be able to give you a really good comparison of, I think this one is the best. Okay, I'm going to stop. I see that there's another question. I'm going to stop here because we're a little bit over time, but I will be available in Remo for answering questions. I will try and find a table. Yesterday I was on floor 3 of the hallway track when I was doing this. So you can find me there if you want to ask additional follow-up questions. Otherwise, thank you for listening. I hope you enjoyed it. I hope you find this useful, and enjoy the rest of CppCon.